Hi everyone, let's talk about our oceans and the atmosphere. Now some of the concepts we're using today we'll bring up again when we talk about the weather. So let's begin with oceans. Oceans help regulate the temperature on land. Now you probably know how hard it is to boil water. It takes a long time, and that's because water has a high heat capacity, which means that it takes a lot of heat energy to raise the temperature of water. Air, on the other hand, has low heat capacity, so you can warm it up and cool it off very quickly. And so what typically happens is that when you're landlocked, the air, let's say over in Kansas, that air is going to change temperature pretty quickly as the seasons change. But if you're in San Francisco, you're right next to the ocean, and it takes a lot of heat energy to change the temperature of the ocean. It doesn't change very quickly. So the temperatures stay pretty constant in the water, despite the change of seasons, and that's going to moderate the temperature of the air. So here's some annual temperatures. So the average in San Francisco for January has a low of 40 and a high of, well, it looks like 55 or so. And let's see, in September, looks like that's the hottest month. It's a little bit more than 70 and a low of a little bit more than 50. So we got an extreme of 40 here to about, I don't know, what is that, 74 degrees or so on average. But in Wichita, Kansas, you can have a low of 20 degrees in the winter and rising up to 40. And then in July, you can have a low temperature at night of 70 degrees and a high of 90 on average. So it can fluctuate between 20 and 90 degrees. That's a severe temperature change as compared to San Francisco of 40 to 74. Here's some pictures of low tide and high tide. What's going on there? Well, it turns out that tides, high and low tides, are caused by the moon's gravitational pull. And to some degree, it's also dependent on the sun's gravitational pull. And here's the idea. You got the moon out here, and the near side of the Earth is closer to the moon than the far side of the Earth. And if we calculate the force of gravity using the law of universal gravitation, the force gets weaker with distance, and not just the distance, but the distance squared. So it turns out that the distance of the diameter of the Earth is enough that the near side experiences a stronger force than the far side, which is weaker, in terms of the gravitational pull of the moon on the Earth. And so because water is fluid, the gravitational pull actually lifts the ocean, pulls the ocean towards the moon. So you get a bulge facing the moon. As it rotates, then there's just going to be a new section of the ocean that will bulge and lean towards the moon. And it's also true the bulge is happening on the opposite side of the Earth. And so you get a bulge on either side, the near side towards the moon and the far side. And then at the sides over here, that's where you get low tide. So we got high tide here, low tide, high tide on the far side, and then we got low again over here. And so as the Earth rotates through one day, 24-hour period, it'll experience 2 high tides and 2 low tides. And here's the tidal forecast for Santa Cruz, in case you want to go surfing. We got 2 high tides and 2 low tides. And these are the changes in the sea level in feet. Okay, the sun has an effect on the tides as well. When the sun and moon are lined up, you get the strongest tides, the highest tides. And when the moon's off to the side, perpendicular to the sun, well, the sun's trying to pull in one direction, the moon pulls in the other. And like I said before, the moon is closer so that the difference in distance is more significant. So you get these neap tides are called when the sun and the moon are at 90 degrees apart, and you get spring tides when they're aligned. Yeah, it turns out this idea of spring tides is not a good name because it doesn't happen just in spring. It actually happens twice a month during each month. As the Earth rotates, it actually rotates at an angle with respect to the sun. So the North Pole is kind of twisted off to the side, leaning to the side. And what effect does that have? Well, 2 major effects. It causes our seasons, summer, spring, winter, and fall. It also affects the length of a day. So let's talk about the seasons. Well, if we look at this lamp here, which is pointing directly at the wall, you can see that the light is fairly concentrated. But when the lamp is placed at an angle with respect to the wall, the light is more diffuse, It's not as strong. It's spread out. And that's what happens on the Earth. So there's a section of the Earth, in this case right here, which is directly being struck by the sunlight. That's this case over here, where the light is more intense. And up here at this part of the globe, the sunlight's striking at an angle, like in this case, and the sunlight's more diffuse. And it's less effective at warming the planet. And so it's cooler. And so we're going to get our seasons, our hotter seasons, summer, when our portion of the Earth is facing the sun. So in the southern hemisphere, South America and so forth, in this diagram, they're experiencing their summer. Whereas in the northern hemisphere, we're at an angle away from the sun. We're getting the indirect light, the light at an angle. We're experiencing cooler temperatures. This is winter for us. But as the Earth orbits the sun, we're going to get different angles. So for us, this is from the point of view of the northern hemisphere, way up here, we're getting indirect light, scattered light. It's at an angle so that we're getting cooler times. And when we're on the other side of the sun, well, now we're facing the sun and we're getting more direct light. It's going to get warmer and we're going to experience summer. And we're at these ends of our orbit. Well, it turns out that the angle of the axis is up and down. And so the northern hemisphere, if it's in springtime, that'll be fall for the southern hemisphere, and vice versa. Now, how does the tilt of the Earth affect the length of day? Well, think about this Earth rotating, and it rotates in this direction. From the point of view of the North Pole, it's going to go counterclockwise. And if you just look at this segment here versus this segment here, you can see that there's a larger portion of the Earth that's in shadow. Yeah, it's nighttime over here whenever the Earth is in shadow. And so how long is it in shadow? A lot longer than when it's in the sunlight. This is winter time in the northern hemisphere when the Earth is at this orientation to the sun. And down in the southern hemisphere, it's summer. And so they get this much sunlight compared to this much darkness. So their days are longer. And then look at Antarctica. It's in daylight for the whole day. And the North Pole in wintertime, it's in darkness the whole day. Okay, let's talk about the greenhouse effect. We saw that before, but now we're going to call it terrestrial radiation. So the idea is that sunlight comes down, passes pretty much straight through the atmosphere, does not get absorbed, strikes the Earth, and the ground absorbs the sunlight and warms up. It uses that heat energy to glow in the infrared, so it's a longer wavelength and lower energy. And it turns out that these wavelengths of lights, the infrared, can be absorbed by molecules in the atmosphere, mainly water, carbon dioxide, and other pollutants. And when these molecules absorb it's not sunlight, it's Earth light, or terrestrial radiation, this glow of the Earth, they absorb it, and then they can emit it in any direction. So if they happen to emit it upwards, well, then that energy can leave the planet. But if they emit it downwards, it can be reabsorbed by the Earth, and then re-emitted, and reabsorbed, and re-emitted, back and forth. And it will keep that heat energy, the infrared light, is a source of heat energy for warming the Earth, and the planet will warm up. It not only warms up the surface of the planet, but also warms up the lower atmosphere. And this is one reason why the air is cooler as you go up in the mountains. As you go up in the mountains, well, you're going into the higher parts of the atmosphere that has been warmed up by this greenhouse effect, and the air is cooler. I always thought that was kind of weird, because when I was a kid and I walked up the mountain, I thought I was getting closer to the sun, and I expected it to get hotter up there. Okay, the greenhouse effect is not being disputed. It's a real effect. But global warming is a little bit controversial. Global warming specifically is the idea that the greenhouse effect is expanding. Or in other words, human activities are creating more water vapor, carbon dioxide, and pollutants. And these are the greenhouse gases. These are the gases that can absorb the terrestrial radiation, the infrared light. And the more gases that can do this, the more greenhouse gases absorbing the light, the more energy that's trapped near the Earth's surface, and theoretically, the hotter the planet would become. Okay, so people have been measuring the amount of carbon dioxide in the atmosphere. We're worried about rising levels of CO2 because we're burning fossil fuels and burning wood and burning natural gas. They all produce carbon dioxide. And as those levels rise, we expect the greenhouse effect to increase. But it turns out that studies have shown, on average, the temperature of the Earth has only increased by 0.7% on average since the 1800s. So what's going on there? Well, one idea is all this extra CO2 is being dissolved in the oceans. And we saw this acid-base reaction. And what's happening is the acid-base reaction is happening in the ocean, creating bicarbonate and carbonate. And it turns out that calcium carbonate makes up seashells. So a lot of this carbon dioxide might be ultimately being bound up in limestone or seashells. But we're also creating a lot more acid, so that's not good. Some other interesting effects is that the polar ice caps are melting. That would suggest the Earth is retaining more heat that's being used to melt the polar ice caps. And then you've probably been aware of other talk of extreme weathers. And that might have been a consequence of human activities, putting more carbon dioxide in the air or pollutants. Okay, let's talk about wind. Wind is simply caused by convection currents. We've got the sunlight that will warm up certain patches of the ground more effectively than other patches of ground, and you'll get a difference in temperature. And where it's really warm, you'll get hot air that rises. Now, the sun warming the surface of the Earth will evaporate some water, so water vapor will travel up with the warm air, and as air rises, it expands and then cools off. And the water vapor that was caught up in that air is also going to cool off. And what does steam do when it cools? It turns into liquid water. And so we get tiny little droplets of water that make up a cloud. Now as this air rises, it kind of vacates the area, and nearby, where there's cooler air, it's going to come in and replenish that air that's leaving. And this motion of air across the ground is wind. And then as this air is moving over to the left, it's going to drag down, but it's going to be replenished by air up above, and that warm air is going to keep circulating over to fill the missing air that's leaving, and you get the circulation of air. Well, how does this correspond to a weather map? Well, we said that warm air is going to rise and expand, get bigger, and it cools off. Now on this side you got the cool air that's going to drop and it's going to get compressed. So what happens when it expands? It cools. Well, then the opposite must be true. When it gets compressed, it warms. And so this warmer air is going to be warming up the Earth, and the pressure is increasing. It's getting compressed. So locally, this area is going to experience high air pressure. And over here where the air is expanding and leaving, you get low pressure. And so you'll see little H's and L on your weather map indicating regions where there's high pressure, meaning in general, fair skies, fair weather, and also regions of low pressure where you get a lot of clouds and possibly storms. Oh, let's also mention the jet streams. So for normal wind, we had regions where there was warm air and cool air, so the temperature difference wasn't that extreme, and we get significant wind from that. Well, the jet streams are created when we get severe temperature changes, like the difference between the polar regions and the tropical regions or the rest of the planet. And so there's a lot of temperature difference, so there's a lot more pressure difference that's going to force a lot more wind to blow and create the jet streams. So essentially, wind is the movement of air from high to low pressure. And normally we would think that the air is going to move in a straight line, right? Newton's first law. But the Earth is rotating. And so what we observe is that the air is going to be turned to the right. What's going on there? Well, let's not move air. Let's move a ball. Think about this playground merry-go-round, this big disc that two kids are sitting on. And we got someone else climbed up in a tree watching the whole thing down below. And let's stop the merry-go-round and just watch the kids throw a ball back and forth, and they're catching it. And as they throw the ball, it goes in a straight line. Well, right before this one boy's going to throw it, we'll put them over here. We're going to give this merry-go-round a spin. And so he throws it, the merry-go-round spins, the ball will continue in a straight line as observed by this guy. But to the two kids on the merry-go-round, it looks like the ball is going to be curving to the right because the ball was thrown here going straight. That's when this one kid was sitting over here, but the merry-go-round moved him to left. Well, as this kid is looking at this kid, he's sitting down. How can he be moving? It doesn't look like he's moving to the left. It looks like the ball moved to the left, to the right. And that's our perspective on the planet Earth. We don't really feel the Earth spinning below us, but it is. And so the wind, as it blows from high to low pressure, it's actually going to be deflected to the right up in the northern hemisphere. It's interesting. In the southern hemisphere, the wind is deflected to the left. This deflection of the air is called Coriolis Effect, or the Coriolis force. And it turns out that all free-moving objects experience the Coriolis effect. So you got air currents, ocean currents, airplanes and missiles, even a snowball, anything else you might be throwing, even though that would be very difficult to detect the deviation of the straight line path, but it's still there. So here we got the globe, and we can think about an airplane trying to fly in a straight line, but then the Earth is going to move out of the way. And so it was aiming for this city as it started its flight, but then the Earth moved it as it rotated, and it looks like your flight path is now swung over to the right. And the farther you are up towards the North Pole, the more severe that deviation. Okay, so what do we know about wind so far? Well, there's regions of high pressure and low pressure, and wind travels from regions of high pressure to low. It attempts to go in a straight line, but then the rotation of the Earth causes it to be bent to the right in the northern hemisphere. And that happens up in the, above the ground quite a ways, upper level. Now if you're at the surface, then you also have to contend with frictional forces of the ground. The wind is going to be dragged on by the ground, by buildings, by valleys and mountains and so forth. And so the winds are actually going to be kind of deflected in all sorts of different directions, kind of to the right because of the Coriolis effect. And that's going to determine how the wind blows. Okay, and here's some interesting maps. If you look at large movements of air, they've actually got some really neat pictures here, trying to combine all these features of the convection currents, hot air rises and cool air falls, and you have these cells here that are doing that. And then we also got the Coriolis effect, deflecting things to the right. And we can talk more about this in class. I'll see you then.